kept the best parts of the previous whiteboard here. We've got vector Laplacian of E is this mess of constants times E. These constants include the frequency component, omega, that we're solving for, permeability, conductivity, and permittivity. And we lump it all together and call it gamma squared. It's a nice little differential equation. When we move it all over to one side and put that constant in there, it's called the wave equation. And it gets better. We're going to cross more things out. Usually the conductivity is 0 in the direction we're going towards objects where there's polymers and glass. They're not very conductive. So it simplifies this expression for gamma a little bit and get rid of the conductivity. And in that case, we can say gamma squared is omega minus omega squared mu epsilon. And when we took apart our expression for plane waves last time, we talked about the wave number, k. And we connected that to this material properties, mu epsilon, square root of mu epsilon times frequency. And we looked at how a feature on a wave moved, and whether it was, usually we looked at how a zero on a wave was moving along, and we got this relationship between your wave number and your frequency that was governed by these material properties. So in this case where there's no conductivity, we have gamma squared is j times the wave number. And we're going to see how that works out by looking at a special case where we propose a solution to the wave equation, okay, where E is just a function of z, like some amplitude that's a function of z only in the y direction. Okay, so I'm getting my vectorness from this unit vector right here. And what that looks like that we've already talked about is this situation where we have a z-axis. And our amplitude is changing as we move along in z. So we can have a sinusoidal envelope, for example. And our electric field always has a y direction, where it's positive or negative is set by this oscillating amplitude. And last time we just dumped this on you. Here's the sine wave, sine E naught sine k z minus omega t. We included some time dependence, so this is just a snapshot at like t equals 0, and it's just moving along. And this is my z-axis in the y-hat direction. Okay, and we're plane waves, blah, blah, blah. But do they work in this system if we actually pull this operator off your equation sheet? This is a vector Laplacian, so it's got 9 terms. And we can split that out into 3 terms that each look like a regular Laplacian. We're used to seeing del squared b equals 0 in Laplace's equation. Del squared e, okay, you take the regular Laplacian, d squared e x, and you take the regular Laplacian of each of the 3 components of e. d squared e sub y, oh, e sub x, yeah, don't let me drift off. So I've got to keep to x right here, and so we're treating this x amplitude as a scalar, dy squared, and d squared e sub x, dz squared, and we're letting each component of this more general E field have dependence on all 3 coordinates, and we're putting that, so this kind of looks like if we had thrown in V right here. We've done that, we've been there. Now I have to move along to the y part, and you can see how this is going to use up all the space I have. All I'm doing in my next term and my z term is I'm swapping this subscript. I'm just going to analyze the y component. Y put that along y hat. And I'm going to do the same for the z component. Why am I erasing the x and z components? Because I only have a y component. This whole thing right here is y. So this is e sub y. E sub y is a function of z right here. Okay. Do I have y dependence? No. Do I have x dependence? No. Okay. Yeah, well, it looks different when you go up in y. Well, what I really need to do, the only thing that's changing here is z. If I move up in y, I've gotten the same amplitude for my electric field. If I took a little sampler and I was able to sample the electric field up here, up here, it would all have this amplitude. It's a plane wave. Okay. So we can knock these things out. Knock them out. On the other side of this thing, well, we'll put it all on one side. Minus, let's see, let's bring that down. Minus, I gotta do jk squared, and I can write this in, e function of z, y equals 0. Okay, and start moving that stuff around. I don't really need these labels anymore. They were handy when doing this, setting this up to map together, and I would actually get 3 equations out of this. Okay, I can deal with this. I got a minus 1 times k squared. So I'm getting plus k squared. Get rid of these parentheses. I don't really need all this punctuation. Okay, and this is looking like what we know and love, complex exponential. So E is some amplitude, e to the j kz minus omega t. We always had that time dependence in there like that. And so I can knock this out and say, yeah, I got this. And it looks like my old plane wave stuff works as a solution to the wave equation. Okay, we write it as a complex exponential, and then it's really easy to take those time derivatives. You should plug it back in and make sure that if you apply this operator to it, you get jk squared times the thing you put in.